It's time for the third talk of this session, and last it's by Andrea. Andrea, you can share your screen.
Yes, hello everybody. Maybe you can see my screen.
It's loading. It's loading now. Yes, we can see the whole screen now.
Okay, so maybe now you see better?
Okay, yes.
Okay.
So Andrea is ready, is eager to start. So Andrea, the floor is yours. Talk to us about enumerating temporal spanners in directed temporal graphs. Thank you.
Okay, hello everybody. This is a joint work with Lapo from University of Florence, Jason and Takeaki. Jason now is at Deep Form and Takeaki is in Tokyo. So this work actually we just presented, actually Lapo just presented at IVOCA and also at DAGSTOOL seminar some weeks ago. So, and these are almost the same slide by Lapo. So thanks Lapo. And this is inspired by our previous work on undirected spanners, so that appeared in SEND last year. So, but before going to talk about the spanners, let me talk a little bit. I don't know how much you are familiar with the enumeration and exhaustive generation. So I'm going to talk about what does it mean design efficient algorithm for enumeration. And in enumeration, what you want to do is not just produce one solution, but producing all the solution. Like you have a graph and you want to produce all the spanning trees of a graph. And what does it mean being efficient? Because you cannot say that it's efficient if it's polynomial, because you are going to list an exponential number of objects. So what you are doing, what you're saying, is being efficient means one possibility is saying that the time between two consecutive output must be polynomial in the input sides. So this is one guarantee that you might you might be happy. Another guarantee could be output polynomial, that it means that basically you are paying a polynomial, a total time, so your algorithm will terminate after a polynomial in both the input sides and the number of solutions that you are going to produce. So, for instance, you are going to have a complexity for the whole algorithm that is n to the c alpha to the k for some constants c and k. And then if you are guaranteeing output polynomiality, then basically, okay, you can get polynomial, if you have polynomial delay, you get automatically output polynomial time, because basically you are paying this n to the c alpha, right? Because if you pay a polynomial for each solution at the end, between two consecutive solutions at the end, this will be the cost that you will get. But sometimes you can be more unlucky, and you can get you can work with problems that do not admit output polynomial algorithm, and actually unless p equal np. And sometimes we prove dual hardness, that it means that basically our enumeration problem is just a transformed instance of a hypergraph dualization problem. That is basically, you can think about enumerating minimal-eating sets. You might know that maybe, minimal-eating sets are you have a given collection of sets, you have elements inside the sets, and then you want to enumerate all the minimal sets that are eating all the given sets. And for this problem, this is, there is not known an output polynomial algorithm, and we don't know whether it's possible or not. I mean, we even under the assumption or p different from np. So this is a big open problem in our enumeration community. And for instance, since we are talking about spanner, let me mention that in the case of static directed graphs, you can do very, very good algorithm. Spanning tree can be listed in this time where n number of edges, n number of nodes, m number of edges, alpha is the number of solutions. So you are paying basically after preprocessing time, constant time per spanning tree produced. So now let's start to talk about temporal graph. So a temporal graph, you heard already since this morning. So it's a graph. You have labels, and we use a standard notation. Okay, I'm just quickly mentioning just to be sure that we have the same notation. So lambda is assigning the time labels, and I call the lifetime, and I denote it with tau. And also I will make use of temporality, that is the maximum amount of time labels that you can have for each edge. So basically this graph has a lifetime 3 because maximum label is 3 and lifetime is 2. Then I'm going to talk about path, walks actually in particular, and I am going to mention these strict and non-strict walks. So a strict walks, it's a walk where the times are strictly increasing, the times of the edges that are traversed, while a non-strict one is is allowing strict walks to be valid, but also a valid walk is the one that is traversing 4 and another 4. So are also the one not strictly increasing. Now let me go to the object that we are interested in, that are temporal spanner. So in this setting, you have a directed temporal graph in input. Then you have a set of sources, so S1, Sk, that is a subset of the vertices. And then a temporal spanner is basically a subset of the edges, such that basically the sources are able to reach every other vertex inside the graph, and this set of edges must be minimal, in the sense that if you remove something, then you will be not able to reach someone. So like you can compute one, so it's polynomial computing one minimal spanner, because just keep removing, okay, the edges and until you arrive to something where you cannot remove anymore. The core represents which sources uses that edge for reachability. So the motivation why in the end you have that. So now basically we investigate several variants, actually 3, one to all. So the set of sources is composed by only one vertex. The set of sources is entirely the entire set of vertex. So basically you want a subgraph of the temporal graph such that everybody reaches everybody. And many to all instead is the variation where you have a fixed number of sources, k, with k greater or equal than 2. So now we have seen that a minimal spanner can be found in polynomial time. And the question is, what about enumerating all of them? And for each of the connectivity constraints, so one to all, many to all, we pose these 2 questions. The first question actually might seem unrelated, but actually is very related to enumeration. And this is called the extension problem. So the idea is that I give you a partial solution, so a subset of the edges, and I am asking you whether you can complete this subset of edges in a solution, in a temporal spanner according to the connectivity constraint. And okay, if you are able to solve this, basically you are able in polynomial time, then automatically you can solve also enumeration, so enumerating on the spanner. And this relies on a very well-known pattern of algorithm design for enumeration that is called in the enumeration community flashlight method. So basically the idea is that for each possibility, you are exploiting the possibility of taking an edge or not taking it. And what is interesting is that in each of the 2 possibilities, you can be sure, doing the check of the extension problem, whether this recursion will lead you to a solution. And this is basically proving that basically you are never going inside the dead end and you are achieving delay, so you are never wasting time. So our result actually are this one, and they almost all of them for strict and strict except for this one. You can see that these are extension and enumeration, the two problems that I mentioned. These are the connectivity constraint, and so let's talk a little bit about this. Okay, so one to all, here you are intersecting, one vertex must reach everybody. So this one, basically, we can prove that the extension problem is polynomial. So given a partial solution, you can decide whether there is a spanner such that contains that partial solution. And then applying the flashlight, you get automatically a polynomial delay algorithm for enumeration. And this is quite interesting because it's the case in which the directed it's easier than the undirected, because in the sand paper, instead for undirected graph, we proved that instead the extension problem is NP complete, but instead so it's NP complete, and in order to make to have an enumeration in that case for an undirected graph, we had to rely on connected extension. So if we guarantee that the partial solution is connected, then it becomes polynomial as well. So this is the first one. Then let me go to the last one, that is instead all to all. All to all, this is basically you want that everybody reaches everybody. So everybody reaches everybody, and in this case, I'm going to show the hardness of enumeration. That it means that I cannot think, unless P equal NP, about an output polynomial algorithm, even with temporality equal to 1. So this is somehow interesting strategy, okay, that we inherited from another paper on enumeration, that is basically transforming a SAT instance in a temporal graph, such that in this temporal graph, that is quite complicated, I'm not going inside this, but basically in this temporal graph, you have exactly n spanner if there are no satisfying assignment for the original formula, but you have at least n plus 1 spanner if there is at least one satisfying assignment. So basically this, this is somehow tricky, but this, what I'm showing is implying that you cannot do output polynomial unless P equal NP. And indeed, why? It goes like this. Basically, suppose that there is one algorithm for our problem, okay, that is output sensitive, output polynomial. So it means that there is a guarantee. The guarantee of the algorithm is going to be NC alpha to the B, right? So because this is the running time. So now, if you let it run for this time, okay, and at the end of this time is still running, it means that the algorithm can afford for this running time, and it means there are at least n plus 1 solution. If it ends before, then you can just count the number of solutions obtained so far, and then if they are n, the formula is not satisfiable. If there are more than n, then the formula is satisfiable. So basically, this is excluding the possibility of output polynomial algorithm for this case. And instead, if we go to many to all, so you can see that we went from delay polynomial to no output polynomial, and what I'm going to present that is somehow in the middle, even in terms of complexity, is the many to all case, in which basically you have two sources and temporality 1, the extension problem we can show that is NP complete. even if the partial solution is connected. So this extension problem is NP-complete, and then we prove that the enumeration is dual hard. Basically, we can transform an instance of minimal hitting set enumeration in a problem of enumerating spanners with K3 sources and temporality 2. So the reduction, basically what it's doing is it has 3 sources. And remember that in minimal hitting set, you have a collection of sets. Here on this layer, you can imagine the elements, okay? Here below, you can imagine the sets. And these connections are making the membership of elements inside the sets. And all the whole construction is made in a way that all edges are necessary, okay? And since in minimal hitting set, you have to enumerate the subsets of this layer to hit all below, the connection are made to make all the black edges mandatory and make only the red edges choosable, okay? So, and the choices of red edges basically will correspond in a one-to-one correspondence to minimal hitting set. So this implies that if you make an output-sensitive algorithm, output polynomial algorithm, for many to all case, then you solve a big open problem in enumeration, because you are providing also an algorithm for output polynomial for hypergraph dualization, so minimal hitting set enumeration. And now, but we go to the positive result that is instead for a very specific case that is polynomial delay for the case with 2 sources and L equal to 1. So temporality equal to 1. Here, the result, it's not, let's say, cannot be trivially solved by flashlight method, because we proved that the checking whether a partial solution can be completed in a solution, can be extended in a solution, is NP-complete. So must rely on some other algorithm different from flashlight. And in order to provide this algorithm, what we do is apply another technique from enumeration that is called reverse search. So basically, reverse search is based on the construction of a graph of solution that basically you don't build explicitly, but it's just implicit, let's say. And this graph of solution is characterized by the fact that for every solution, for every spanner in our case, there is only one parent. That it means the parent intuitively is the other solution that by applying some operation will be able to produce the new solution. Okay, so you define this parent-child relationship between solution in a way that each spanner have only one parent. And then basically what you have to do is to design also the opposite operation, then giving a parent producing polynomial time all the children, polynomial for each of the children, all the children of the parent. And so basically then the algorithm, how it proceeds is just using this neighboring rule. Basically, you are navigating this graph of solution, passing from one solution to the other, like you would do in a depth-first search. And there are some additional detail to get memory polynomial, but I'm skipping this detail. I can tell you more if you're interested. So you have to start from a from a root, okay, from one solution to start the DFS in the graph of solution, and the root discovery, it goes like this. So you start each time, you basically, since there is a total order, because we are assuming that L is equal to 1, there is a total ordering of the edges. So you process the edges in the order, and you include in the partial solution if they are increasing the reachability. And you can see that I put 1 and then I'm putting 2, because both these edges are increasing the reachability, in particular of S1. Then I'm inputting 3, I'm processing 3, and this is also increasing reachability, so it's improving my partial solution. Then I'm putting 4 because also this is good, this is improving my reachability, but then, be careful, here I'm putting 5. 5 is bringing me to remove 4, because 4 is, if I will keep 4, then I would violate the minimality constraint. So there is some cleaning involved in which if 5 is improving, then because indeed 5 is improving, is letting S1 to reach one guy more, so I have to clean something else. And we have a cleaning procedure that is taking care of this. And then you keep going, like you can see that after 5, I'm not including 6 because it's not improving. 7 is improving, 8 is improving, 9 is not improving because it's reaching something that is already reached, 10 is improving, 11 is improving, and then I finished. So this is my root solution. Starting from this, now I will navigate the graph of solution. And actually, I can do a similar reasoning in order to do this, to starting from some given arcs. So instead of starting from an empty, I start from some given arcs, and I apply this strategy that this actually corresponds to a completion of a partial solution, which in the case of the root, indeed, was starting from an empty set of arcs. And be careful, this is not an extension, because we proved that extension, so producing a solution that is keeping the given arcs, is NP-complete, because we were removing stuff. Like in the example that I show you, I removed the edge labeled with 4. So the parent, now, the neighboring in the algorithm between solution is done in a way that, for instance, this is, just trust me, this is P, R and S. R and S are the children of P, and are children of P. Why they are children of P? Because in their, let's say, canonical representation, that is the ordered set of the edges that are composing them, the parent of R and S is P because their maximum prefix, so I start from the end and I apply the complete procedure, the completion procedure that I show you, and it's the first time that I am reaching something different from themselves. So if I do like completion from here, from here, from here, basically I'm obtaining always R. But if I'm doing completion from 3, for instance, okay, I'm getting something else and I'm getting P. And the same is happening for S. So is actually the first time starting from the right where I'm applying the completion procedure, I am obtaining something different. So the parent, this is basically the parent, defining the parent given a children. And now, to complete the algorithm, I have to provide, given a parent, all the children. And this is basically a non-trivial task that, if you are interested, I can tell you more, or you can look at the paper. So basically, this is all. And now what we are doing is adapting the algorithm for enumerating many tools. 2 sources, any temporality, and any sources, temporality 1. So we basically, I show you in a very specific setting, 2 and 1, and this can be done we're thinking that it can be done because you still have the total order between the edges because of this temporality 1. But this one is tricky because now you have to look, you can still define a total order of the edges, but now the edges can have many labels, so this total order is more tricky to define. So that's it. So thank you very much for the attention, and thank you.
Thanks, Andrea, for the talk. Any questions for Andrea? Okay, I have a very quick question here, So I think it's similar to the spirit of the question that I've asked previously to Niels. So do you think there is any structural property that can allow us for the problems to become easier for the enumeration?
Okay. Yeah, I mean, that's the polynomial algorithm that I was showing. So the fact that temporality plays a role, for instance, in this, right? It goes in this direction in some sense. And I don't know if there are other parameters to be investigated, and then that might make the things easier. So we don't know, but I think it's interesting independently from what we are doing.
And Arnaud has a question in the chat.
Yeah, let me read it. Okay.
Okay. If you did experiments, did you use any fancy algorithm for testing minimality?
Been searching for one. No. Actually, we didn't do any experiment.